Every swirl of smoke, every churning ocean current, and every turbulent wake in nature follows a specific, predictable logic. No matter how chaotic a fluid appears, its motion is governed by a universal set of mathematical rules. These rules are the incompressible Navier-Stokes equations. They describe the conservation of mass and momentum for every point in a flow field across all time. When we solve these equations directly, without making any approximations, the process is known as direct numerical simulation, or DNS. It tracks everything from massive building-sized swirling eddies down to the microscopic scales where kinetic energy is converted into heat. Because it requires an exact accounting of every spatial and temporal scale, DNS represents the uncompromising standard of computational fluid dynamics. It is technically perfect and largely inaccessible for industrial engineering. The barrier is computational cost. As the speed or scale of a fluid increases, a value called the Reynolds number, the turbulence intensifies. To resolve those microscopic fluctuations, the required computing power grows exponentially. An academic DNS simulation of a tiny box of air can take weeks on a high-performance cluster. Attempting to run a DNS over a full-scale aircraft or a wind turbine would increase the complexity by several orders of magnitude. Simulating high Reynolds number industrial flows with DNS would require supercomputers that do not exist today and likely won't for years to come. To make CFD practical, engineers cannot track every microscopic fluctuation. Instead, they calculate the time-averaged behavior of the flow. While averaging makes the physics computable for modern hardware, it leaves the system of equations underdetermined, a bottleneck that has defined fluid dynamics for a century. The process begins with Reynolds decomposition. We take the instantaneous velocity of the fluid and split it into two parts, a steady mean component and a chaotic, fluctuating component. Applying this to the Navier-Stokes equations creates the Reynolds averaged Navier-Stokes, or RANS, equations. The result is a smoothed-out velocity field that is much easier to solve, but the nonlinear nature of fluid motion creates a complication. When we average the equations, the interaction between those chaotic fluctuations manifests as a completely new, unknown mathematical term at the end of the expression. This is the Reynolds stress tensor. It represents how the discarded microscopic fluctuations influence the visible mean flow. Since we no longer simulate the fluctuations, we cannot calculate this stress directly. We now have more unknown variables than equations to solve them. This is the closure problem. To solve the simulation, engineers must use external models to guess the value of this missing term, an act known as closing the equations. The standard solution has been the Boussinesq assumption. This model attempts to guess the Reynolds stress by using a concept called eddy viscosity. This assumption simplifies the physics by modeling the unknown Reynolds stress as a direct result of the mean flow gradients. Turbulence models like k-omega use additional transport equations to calculate this viscosity. They provide a rigid, simplified approximation of how turbulence behaves. These equations rely on empirical constants, numbers derived from specific isolated experiments like flow over a flat plate. While computationally efficient, their reliance on simplified assumptions often leads to inaccurate results in complex, nonlinear flows where those assumptions break down entirely. Instead of relying on manual empirical guesses, we can replace the closure equation with a data-driven formulation. Here, a neural network is designed to learn the relationship between the local flow features and the unknown Reynolds stresses. Tensors of the local flow gradients enter the input nodes, and the network predicts the corresponding Reynolds stress at that specific point in the fluid. To ensure these predictions obey physical laws, the network is constrained by Galilean invariance. It outputs its predictions in a coordinate-independent form, ensuring the fluid behaves consistently regardless of the frame of reference. The AI doesn't just calculate a number, it learns to approximate the underlying nonlinear physics of the stress tensor directly from high-fidelity data. The training data is extracted from high-fidelity DNS. The neural network learns by analyzing the exact stress patterns present in these computationally expensive simulations. This training happens offline. The heavy computational work is completed before an engineer ever starts their own project. Once trained, the AI model is integrated into a standard CFD solver as a plugging, replacing the traditional k-omega equations. The engineer gets a solver that maintains RANS-level speed while incorporating the complex stress correlations learned from high-fidelity DNS. Comparing the same flow computed differently, the RANS simulation on the left is overly smooth. It misses the complex nonlinear vortices of the central DNS target. However, the AI model on the right predicts accurate stresses, capturing structures that classical modeling obscured. Data-driven closure is not a universal solution. Classical models remain fast, robust, and physically interpretable. When they fail, the underlying equations are transparent. AI models are data-heavy and can be black boxes. They often fail to generalize when applied to flow conditions that were not included in their original training set. However, for complex engineering challenges within the network scope, data-driven closure provides the most significant increase in accuracy for CFD in several decades.